Oh, goody. So the first thing I want to talk about was something that Janessa brought up yesterday in tutoring. And she is one of the many people I was not very nice to. So first, apologize to Janessa. Sorry. I was not very nice to you. I was not very nice to anybody, but I was really mean to Carlos. But Carlos isn't my student, so I don't have to worry about it too much. He's, Carlos shows up religiously to every single tutoring session. I've never met the kid, but he comes all the time. You have to connect all the dots. That's the biggest thing I want to impart to you. If I asked you that when I lift an object, does its potential energy increase? And I say, explain why. You can't say because it got higher. There's more to it than that. You have to make sure I understand that that potential energy is calculated based on MGH, and that H represents how high it's been lifted. You know what I mean? You have to connect all the dots. So if I say something's traveling at 5 meters per second, and then later it's traveling at 10 meters per second, and I ask you if it's kinetic, how do you know if its kinetic energy is increased? And you say because it's going faster. That's only half of the answer. The other half of the answer has to demonstrate that that velocity and kinetic energy are related. You can't assume that your person who's grading it is going to make that connection for you. I mean, yes, it's true that in their head, they know that kinetic energy is 1/2 mv squared. They're not being tested though. You are. They want to know that you know that. So you have to say, well, kinetic energy is proportional to the square of the velocity, or kinetic energy equals 1/2 mv squared. So if I'm comparing two things and one of them's traveling faster, then you have to make the comparison. You have to say the two things have the same mass, but the one that's traveling faster has more kinetic energy because, and that's where you state it. Simply picking one isn't enough, even if you say it's because it's moving faster. So, and Janessa pressed me on that a little bit last night, indicating, well, what things do I have to say specifically? I think if we want to pass the AP exam, and that's what we want, that's what I want. I don't know if you want it, but that's what I want. So if I can get you to state all of the different connecting points, I think that guarantees there's no wiggle room from the graders. I don't want them to get a bug up their butt and decide whether they can give you a point or not because they don't like the way you said it. Don't make it about that. Make it about saying all the things so you leave no ambiguity. So you just can't make an assumption. You can't assume that I know any physics. You are explaining it to me. I think that's the best way to go. So if there's anything in your explanation that requires that I know something about physics, it's not complete. Now that does not mean I need 5 extra sentences. It means I need one phrase in there that indicates that that kinetic energy is proportional to velocity squared, that kinetic energy is proportional to mass. And don't leave out the mass part either. If I say I have 2 objects that are going the same speed, but one of them is twice as massive, well, one of them has more kinetic energy. Why? Because it's also proportional to the mass. Do you see where I'm going with all that? Have I talked it into the ground now? Because, look, I inputted your test grades yesterday because I don't know why I sat on it for so long. There's some of you who need this, right? Your test last time might not have been a good reflection of what you're doing, and it's because we bean count these points. We nitpick them. That grading day, everybody's unhappy. Well, not everybody, but a lot of you are. And it comes right down to these little tiny things. Tomorrow, this question isn't on the test tomorrow, but one like it is. So it says at the start of the ball, more potential. Believe it or not, that's a complicated answer. And you probably don't understand why, but let's just say that a person had to lift the ball and put it on top of both ramps. Assuming both balls were stored in the same place, they probably did the same amount of work lifting the balls up to that same place on the ramp. You could make the argument that both balls have the same potential energy, and it would be a fine argument because the same to the top of the ramp. You guys understand? I want you to consider all the things that are on your tabletop. The same amount of work was done getting all of them up there, assuming they were all the same mass. Because you all had to take them up the stairs, you all had to bring them in the room, you all had to get them out of your backpack and put them on the table. But if one of them is right at the edge of your desk and is about to fall off, and one of them is in the middle of the table, does one of them have more potential energy because it's about to fall? It's a weird question, because in these problems, we are basing the potential energy when we try to calculate how fast it's going based on how far it could fall. Could is a pretty ambiguous word, wouldn't you agree? So I think if you want to answer this question correctly, you have two choices on how you answer it. First, you can talk about the work done in lifting the balls and placing them at the top of the ramp. I think that would be a fair argument and would indicate that the amount of potential energy they have is equal because they're both brought from the same location to the top of that ramp. But I also think you could make the argument from the context of conservation of energy, that they're both about to roll down a hill or a ramp. One of them could clearly go a greater change in height than the other. So from the standpoint of them about to roll, the ball on ramp B has more potential energy than the ball on ramp A because its reference level is likely lower. Both answers are arguably fine. You have to be the one to convince me of which one you're discussing. So if you're discussing conservation of energy of the balls about to roll, then I would say ramp B, because that particular ball has a farther distance to go and potential energy is based on the height. All of those things. Yes, ma'am.
So even though, so they're at the same height, right? Like right now, like what in the picture, they're at the same height.
They're at the same height, sure.
So it has more, the second one has more potential energy because it can go lower.
It's this, the reference level. If I was to release each of these two, how would you figure out how fast this ball is going compared to this ball? How would you do it if I asked you to calculate it? I would agree. So in this case, I'd have 1/2 mv squared equals mg h minus h naught. And this one I'd have the same thing, right? Oops. Now, on which side would this part be bigger? So I think you can make a reasonable argument that from the context of the ball rolling down the ramp, ramp B has a ball with more potential energy than ramp A, of where it could roll to. The word could very specifically. So I think in that context, you could say that the ball has more potential energy. I'm being very diplomatic here because you could make the other argument and it would be just fine as long as you are clear about the context. I'm not trying to mince words here. Don't make this harder than it is. If you say both balls were lifted to the same height and you say that, and then say that potential energy is based on how high you are and your mass, then you are likely going to get the right answer because you are being clear that from the standpoint of the same reference level, they both have the same potential energy. But if you are talking about them rolling down the ramp, ball B has more potential energy. Free and clear. Yes, sir. Yes, I think you would. I think you'd have to state what you mean by the reference level in context to MGH. I think as long as you do that, though, you're fine. Does that make sense? Okay. All right. That was only part A. I don't want to belabor it too much because I can't imagine that's going to be worth all that many points compared to the whole problem. So let's move on a little bit. Is either ball traveling faster when it makes it to point P? No. No. They're all the same change in height. When they make it to point P, they have had the same change in height, so they're going to have the same amount of kinetic energy. Questions about that? All right. Does either ball ever travel faster than the other one? Yes, the one on ramp B does. When it's at the lower place, it's going to be traveling faster, which likely makes it for question D to be that ramp B suggests that ball might be able to make it to the end sooner. Why? Because if you're traveling faster, you cover more ground in a less amount of time. That's exactly what Janessa said. I'm just kind of quoting her from yesterday. The one that goes faster will get there sooner. So it is quite plausible the one on ramp B will get there sooner, even though it has a longer path. I want to point out the path for ramp B is longer than the path for ramp A, but the speed that it gets to travel at is higher. That's a lot for situation one. This was right off of an AP exam a couple years ago. The only difference between this problem and the one that was on the AP exam is part E, F, and G, where the ball rolls off the edge of the table and becomes a projectile. And they talk about the projectile part of this problem right after it. So just be aware, this is just first half. Yes, sir?
If we were to see a question like this on our test tomorrow, would it be like, would it get the curve that we usually do, or would it not be? Like the AP curve that you said, you get if it's like a question that comes from an AP exam?
I will only do the curve if I actually give you an AP question or one that is very similar to an AP question. I'll give the AP curve. So this one is only half the question, so probably not. Not to mention, I've told you, I mean, you're not going to get this one.
I mean, like a question like that.
Maybe. I'm going to give you a solid maybe. And this is not just being a jerk, but since you won the debate, and I don't want to debate you because you're probably very good at it, and we should all congratulate Noah. He won a debate contest last weekend. So I have to be very careful about debating you because you'll have your facts straight and I won't. I don't like any student going into the test thinking they're going to get a curve. I really don't. It never works. And I'll explain. The curve on the AP1 exam changes every single year. It has not been consistent once, meaning the cut points have never been the same. So how do I tell you how many points you need to get in order to get an A on the test if every year it changes? Do you understand where I'm going with that? So, and we have no data on last year's test, none. So I have no way of even explaining to you, even though it's like 15 different problems, how they were going to deal with the grades. We have it was like a mystery box. They put everything into a machine. It came out 1, 2, 3, 4, 5. AP like mechanics is different. I know exactly how many points you got to get a 3, 4, and a 5. I mean, exactly the number of points. It hasn't changed in about 12 years. So there's the difference. I don't mind curving their test every single time because I know I'm using nothing but legitimate test questions. Here, the questions have been so flexible. Some of them I think warrant the curve, some of them don't. And I know that's a pure judgment call and you would like me to be more particular. I'm not going to be. Not because I don't want to, it's just because I really don't know. I usually take a look at the entire average of the class, make a judgment about how students perform based on that. Just so you know, I've been breaking it up too. So I look at how the students at home perform compared to how students in class perform. I run stats on the numbers a little bit and then see if there's any significant differences. And then I look at compared to how students did on the test last year. I do a little bit. That's why it takes even longer to put it in because that's how I kind of decide. Okay. Any other questions on this? Yes, ma'am.
Sorry, for question number 1, part B states that is either ball traveling faster when it makes it to point P. Would that be the same because of the fact that they have the same reference level at the end?
Yeah. I mean, if I was to do conservation of energy there, I would use H for both of them. The H that's given there. Just set that as a reference level. All right. Any other questions on this practice? Yes, ma'am. Yep. I'd be happy to go over the elevator question. I don't have room here, so I'm going to go to another page and do the elevator question on another page. So, and because I'm on the other page, I can't see the question. So, but this has an elevator and it's experiencing 2 different forces. It's experiencing an upward force due to tension and a downward force due to gravity. They tell us that the elevator travels a distance, is it 10 meters? Is that right? Down here, I'm assuming that started from rest. It does? Okay, I didn't switch back to the problem to know. And when it gets up here, it's moving, is it 4 meters per second? All right. How much net work is done? That's question A, I believe, or total work. Total work is another word for net work, which is going to be the change in kinetic energy. That's all you have to find for this one. So it's a 1,500 kilogram elevator. So the net work done is going to be 1/2 times 1,500 times 4 squared minus 0. This is the net work done on the elevator by all the forces. And I don't know what this is, but probably pretty big. Is it 16? What's that? 12,000. 12,000 joules. So the second question is, consider all the forces that act on the elevator. Which forces do work on the elevator? If I consider all the forces, well, tension and weight do work on the elevator. We don't know anything about air resistance or anything like that, so I'm going to neglect those and say tension. And tension does positive work on the elevator. Weight does negative work on the elevator. Yes, sir?
Would you have to say weight there, or could you say gravity?
I don't think it makes a difference. Let's see. How much work does each force do on the elevator? Make sure to indicate whether the work is positive or negative. We don't know the size of the tension force, but that doesn't mean that we can't figure out how much work the tension force does on the elevator. And I'm saying that because we know that the work done by tension and the work done by gravity has to equal 12,000 joules. And some has to equal that. So let's find out the work done by gravity first, and then we'll be able to figure out the work done by tension. The work done by gravity is going to be, remember, we have 3 buckets here to calculate work. So the first bucket is the force that acts on the elevator. That's the weight, mg. So that's going to be 1,500 times 10, or 15,000 newtons. That's the force of gravity. Gravity acts over a distance of 10 meters. And it acts downwards, but the elevator went upwards. So that is a cosine of 180 degrees. So that's the work done by gravity. I don't know what that, 150,000, but it's negative. So if I want to figure out how much work was done by tension, I'm going to say the work done by tension minus 150,000 has to equal 12,000. I'm just using the work energy theorem. I solved that for the work done by tension. Now swing that around, I think I get 162,000 joules. Questions about that? I like these kinds of questions. You should expect it on the test tomorrow. What was the tension that acted on the elevator while it was accelerating upwards? All right, well, the tension that acted on the elevator requires that I kind of take what that didn't work. I take what I just used and kind of find the tension. I'm going to say that the work done by tension has got to be equal to, the 3 things. This is 0 degrees because it acted upwards. This is 10 meters. And I don't know what the tension was. But I know that this all had to equal 162,000 joules. So 10T equals 160,000 joules, or T equals 16,200 newtons. You did not have to do it this way. You could have found out the acceleration of the elevator and done net force. And just to make sure, I see your hand, but let me finish my thought. I know the initial velocity was 0. The final velocity was 4 meters per second. The displacement was 10 meters. Therefore, if you use a formula here, I'm thinking v squared minus v naught squared equals 2a delta x. You'd get that a is 0.8 meters per second squared. Net force equals ma. So tension minus 15,000 equals 1,500 times 0.8. Lo and behold, tension equals 16,200 newtons. So, I mean, you have more than one way to do it. I'll remind you, V squared minus V naught squared equals 2A delta X. That is the work energy formula as a motion equation. So it's going to be the same stuff. You're going to use the exact same mathematics. It's just whether you think of it as work or you think of it as a motion equation, it's all the same. Go ahead.
So if we use the acceleration in the last problem, can we just say C work above?
Yeah.
Or- okay.
Okay, there's more to this question, isn't there? The work done against gravity is stored as potential energy. After the 10 meters has been traveled, how much potential energy does the elevator have? How much kinetic energy does the elevator have? This is a redundant question. And it's just to see if you can make the connection. And this, what I'm about to say right now, I'm just going to put this big white box over everything so I have a place to work. This isn't to confuse you. It's just so that you understand when you do work against a conservative force, it is stored as potential energy. The work done will be negative when you do it against a conservative force. When you do work against a conservative force, the work done will be negative, right? Gravity acted downwards, but the box went upwards. Work was being done against that force. So we say that the change in potential energy is equal to minus the work. This is the mathematics behind it. This would be something that would be more important if you were in mechanics than in this class, but it's still true today. This is why we say potential energy is just mgh. We don't have negative forms of energy when we deal with conservation of energy like that. So this is going to be, the 1,500 times 10 times 10, or 150,000 joules. We already know the answer. The work done against gravity is stored as gravitational potential energy. And the kinetic energy we found already was the 1/2 mv squared, which I don't remember. 12,000? Is that right? Joules. Yeah. So those are just the answers. I mean, we already did all the work for this. All right, 9:03. We still have time. Want to do any others? Any other ones of these? Yes, sir. Part B of which one? I'm sorry, I couldn't hear you. Sure. Let me make sure. Is there anybody who needs to see part A of situation 3? Okay. I had a feeling. All right. So situation 3. Patience, Iago. All right, so this is 4h. This is 3h. The car starts down here with a velocity v. I'd like to know the minimum velocity necessary to make it to the top of the ramp. I think that's what the question asks. Find the expression for the minimum speed of the cart in order to make it to the top of the first hill. To make it to the top of the first hill, if I look at this picture clearly, to make it to the top of the first hill, I will have to have a potential energy equal to mg times 4h. This is how much energy I'm going to have to make it to the top of the first hill. If I have less than this, then I make it here something not as high, and I'm not at the top of the hill. If I have more energy than this, then the remainder will be in kinetic energy, and that's more than I need. To make it to the top of the first hill, I need the minimum velocity. That's what they said. What is the smallest velocity I can have? And that's going to be the one where mg times 4h is equal to 1/2 mv squared. You guys can't see that because it's all way too high, so okay. That's it. So solve for v min. Yes, Rachel.
So the reason that it's just the gravitational gravitational potential energy equal to the kinetic energy is that if it so I thought you're supposed to have the kinetic energy at the top as well, but you don't use that because you just want it to just make it to the top and not keep going.
Yep. Yes, ma'am. I'm not going to be that particular about it. If I want to make it over the hill, the truth is I need to have a little more velocity than this. But if I have this, I at least won't roll backwards. So you just cancel the m's and solve for v now. Your actual answer should be expressed as the square root of 4gh. So question B says, the spring constant K is located on the landing on the opposite side of the hill. What is the speed of the car just as it makes it to the spring, assuming it successfully just made it over the top of the hill? This assumes we had enough velocity to make it to the top of the hill and maybe just a little bit of a skinch more and we go around the corner. You don't add more energy to this. We assume that this is still the finite amount of energy that we have. Okay, there's 3 hands up. So what did I do wrong here? Oh, I forgot the 2. Sorry. This should be 8. So I assume all of you are about to correct me. Thank you for reminding me about the 1/2. Appreciate it. When 3 hands go up, that usually means Michelle made a mistake. So nobody likes to jump on it better than students to show that I made a mistake. So I appreciate that. Keep me honest. Keep me honest. Yeah, I'm gonna take this off here. There. All right. So, anyways, we're gonna still work with this amount of energy. I'm saying that this is the amount of energy that we have when we make it right here, and we are right next to, but not compressing the spring. We want just the velocity as we hit the spring. So at that point, we've got gravitational potential and kinetic. There are other ways to do this. You could have reset the reference level, made the reference level the 3h. It gives you the same answer. So I don't want to argue about you saying, well, what if I set the reference level here? Good for you. So this will be mg times 3h plus g times 4h. Do a little subtraction, solve for v. That's how fast you're going to hit the spring. So pretty sure we're going to have v equals the square root of gh. The only difference between this question and the next one is we hit the spring now. The spring takes away all of this kinetic energy. Doesn't take away any of the potential energy we have, but now it's something like that. You guys, you could turn on that back projector if you'd like. I didn't even bother. I'm sorry. So, but I mean, we're just going to solve this the same way, except this time we're solving for the spring constant. So I'm going to subtract the mg3h from both sides, get 1/2 kx squared equals mgh, and then just solve for k. Or no, I solve for x. You want to know how much the spring is compressed, so solve for x. So x is going to be equal to 2mgh over k, and then take the root. And my head's in the way. Nobody needs to see that. Good? Questions? Yes, ma'am.
I'm sorry, can you do the algebra for the equation on the left?
Okay, I probably forgot the 2 again. Surprised I didn't see all sorts of people throw their hands up in the air to remind me that I forgot the 2, but that must be what's going on here. So 1/2 mv squared equals mgh. I clearly canceled out the m's, and then I clearly multiplied by 2 on both sides. You just didn't see it. And then I clearly took the square root. So clearly, take a day off and everything goes to pot. All right, so is the next question about circular motion? Yeah, so this time the car returns, run from the spring. The spring is pulled back far enough for the car to make it over the hill. The hill, however, is circular at the radius curvature of h. What is the maximum speed the car can successfully make it over the hill and not lose contact with the ground? That has very little to do with all the stuff that's here. So because it has very little to do with all the stuff that's here, how about we get rid of all the stuff that's here? This is a new problem and is about circular motion and is not about this part of the energy problem. I am going to change things a little bit and set the reference level to be where the spring is. And we're going to say that this has a radius of curvature of h. Any questions about that? Potentially there are two forces acting on the car, a normal force upwards and weight downwards. There's no way around this. So net force equals mv squared over h, where h is the radius. I have to set my direction towards the center. So mg minus n equals mv squared over h. I'm gonna have no patience for people not being able to do this. The maximum speed occurs when the normal force goes to 0. I can go slower than that, just can't go faster. Because judging by this is a constant. This depends on velocity. So as v gets bigger, since this number can't change, this number has to get smaller. So the smallest we get is when n goes to 0. That means that v max, and this time I didn't forget the 2, is just square root of gh. Now your next problem, how far can you pull back the spring and successfully make it over the hump without losing contact with the ramp? This one's a conservation of energy question. Down here, we're going to have 1/2 kx squared. On top of the hill, we're going to have mgh, because we are 1 meter above the reference level, plus 1/2 mv squared. We have to substitute what we got for v in the prior section of the problem. So that's going to be 1/2 mgh plus mgh. That's 3/2 mgh times 2 is 3 mgh. So x squared is going to be 3 mgh over k. So take the root. And that's what you got to do. Whee! Whole lot of expressions here. That's a little heavy for your test tomorrow, but not out of line. My feelings, this is in line with what you should be capable of doing. Again, it's a little heavy, heavy with the algebra. Yeah.
When you set the reference level and you have to explain something, as if it's in an FRC, did you say you were referencing?
If you're asked to explain, yeah. But you would have gotten the same answer if you had not reset the reference level. So I don't know that in this problem that, unless they specifically ask you about the reference level, I don't know that you have to explain that you did that. I mean, the only difference would have been that you would have had a gravitational potential energy here, which would have been mg times 3h. And here would have been mg times 4h. So you would still have the same, the answer's the same. You're just adding 3h to both sides. All right. It is 9:14, which means I still have time. Is there anything else on this you would like to review? I would like to review something because you're not thinking of this, but I am. And I want to talk about this picture at the bottom here. If I wanted to throw you a curve, this is what I would ask you. If I wanted to see if you can adapt, this is what I would ask you. And trust me, I don't think half of you will adapt. I think half of you will freak out. And I'm kind of counting on it, not because I'm a jerk, but because I'm trying to see if, I'm worried you guys can't adapt. Right now, I can't adapt, apparently. All right, so I have a plot of energy And I have this picture of this system where I'm going to pull the spring back a distance negative d. What would the energy versus position graph look like for this? I want from just negative d to 0. And I want you to think about it because I think you're going to get this wrong. But I think you should know how to do this. And I'm going to be frustrated because many of you won't think of it this way. So jot a quick picture of this. What would just the energy from the spring look like? You guys at home have a chance to do that? All right, now, if I had more than 3 minutes, I'd walk around. I don't have more than 3 minutes, but the energy of the spring should look like this. And it's wrong if it's anything else. And I'm seeing all those erasers come out. Yep, you're wrong. And you're wrong because you don't think of things like this, but it is 1/2 kx squared. The horizontal axis is position. So it says that the amount of energy I have is proportional to the square of the position. It's that simple. When it's at 0, x is 0, there's no potential energy. When it's at negative d, the energy is 1/2 k times d squared. That's where it starts. Now here, I'm gonna screw you over a little bit more. What does the curve for the kinetic energy look like when I release the block? You don't have an equation you can use for this, by the way. The only equation you have is based on velocity, not position. So whatever shall you do? But I think you should be able to know that the energy stays constant, which means that as it loses potential energy, it gains kinetic energy. It should be the opposite of what we just drew in order to make sure the sum stays constant. They're going to cross somewhere right in the middle, but the sum has to be constant. There should be like a line up here at the top that the energy stayed the same. The yellow line represents the total energy, which is a constant. If I asked you to graph the total energy, you would just draw a straight line until it hits the friction. I don't think you think like this. Whoever's getting signed out, this is annoying. Shelton's House of Pain. I'd be happy to. Andrew Lambert, you're requested to go to band when the bell rings. Yeah, you're looking at the wrong person, but how does this continue? What happens after this? How would you draw the rest of it? You should be able to. I know you guys, think it's the end of class, but I got, 30 seconds. Now it's linear. Why? Work equals friction times distance. Friction's a constant, mu times a normal force. This is linear. The work done by friction is linear. It's proportional. I double the distance, I double the amount of friction. The work done by friction. So, yeah, if I wanted to mess you up, that's what I would ask tomorrow. I won't ask this one now, but I got lots of them. Lots of them. See if you can, think on your feet. This is the difference between a 4 and a 5 is what I kind of think of. All right, folks. Study tonight. I have nothing more for you guys, but study tonight. See you all tomorrow.